And welcome to 3.4. This section is on density. It's one of the fundamental properties that matter has. And the first thing we want to talk about is what density actually is. All density is the ratio of the mass of an object to its volume. How much stuff is crammed into a particular volume or a particular space. Here's the equation that describes density, and that's an equation you'll be able to use on any test quiz or the final exam. Now the deal with density is that it is an intensive property because it only depends on the composition of that substance, not on the size of the sample. Gold has a particular density. It doesn't matter if you have a little bit of gold or if you have a block of gold. Water has a particular density, whether or not you have a drop of water or Lake Erie full of water. Its density is the same regardless, as long as we're talking about pure water, pure substance. All right. Now scrolling down. Typically, when we're looking at density, oftentimes people are misjudging the weight with its density. For example, if you have three objects that all weigh the same, in this case you have lithium metal, water, and lead. Most people say that lead weighs more than other objects. Well, that's because it is very heavy for such a small object. If you look at the comparison here, lead is more than 11 times more dense than water, and it's going to be pushing 20 times more dense than lithium. So this is why it gives the connotation of being heavy, is because you have so much mass crammed into a small area, which leads to the age-old question, which weighs more, a pound of feathers or a pound of lead? Well, the fact is, if you have a pound of feathers and a pound of lead, they weigh the same, except the lead might be just a small little block where you might have a huge pile of feathers to equal that pound. All right, so you want to keep that in perspective. So that's that. Moving on. Here's a nice little table that describes the density of some common materials. Notice the density of gold. It is a very, very high density, a lot of mass in a given area. Compare that to lead. Most people, if you've ever, when you go to a doctor's office and you get an x-ray, or maybe even at the dentist's office, they'll put that lead vest on you, and you'll notice how heavy that lead is. Well, lead has a density of 11.4 grams per cubic centimeter. Gold is 19. It's not quite twice as dense, but it's quite a bit more dense than lead is. All right, and that goes back to the question we had before in 3. Water is down further on the list. Water has a density of only 1 gram per cubic centimeter, and so if you want to put that into perspective, when you pick up a gallon of water, it has a little bit of mass to it, but as we calculated in 3.3, when you pick up a gallon of pure gold, it's going to weigh over 160 pounds. So density does play a huge role in the properties of the matter that you're talking about. All right. The other thing that density allows you to do, or the other thing that density affects, is which objects or which liquids or which gases float on top of others. The deal is, the more dense excuse me. Again, the more dense an object is, the lower it's going to go into a column. The less dense it is, it's going to tend to float towards the top. It doesn't matter if you're talking about liquids or gases. The more dense a gas is, the more it's going to sink towards the floor. All right. So as we scroll down here, here's a question: if the graduated cylinder above was filled with ethanol, water, gasoline, and corn syrup, which layers would correspond to which liquid? All right, so let me kind of change some colors here. We'll stick with orange for the water. Water has a density of 1. If you take a look at, say, ethanol. Ethanol is down here at a density of 0.789. The gasoline, if we go with the red, the gasoline is going to have the lowest density at somewhere between 0.66 and 0.69. And finally, the corn syrup. The corn syrup appears to be the most dense at somewhere between 1.35 and 1.38. So since corn syrup is the most dense, the corn syrup is going to sink to the bottom. All right, followed by the water. The water is the next, has the next highest density, and so that's going to be here in layer C. All right, the ethanol is less dense than that, and so it is going to be here in layer B, and then layer A is going to have to be our gasoline, since it is the least dense, and so that's how it would pile up. All right, so density affects where they would layer in a column. Okay, scrolling down. Now, the density of a substance generally is going to, and I'm going to change back to the orange here, is generally going to increase with increasing temperature. I'm sorry, it's going to decrease. Density is going to decrease with increasing temperature simply because the volume increases. What happens is that materials tend to expand. Well, if you look at the equation where you have density equals mass over volume, if the object is going to expand without changing mass, that means that this denominator is going to increase, which means that this whole fraction is going to have to decrease. And because of that expansion of objects and the decrease in density, you have to account for that when you're using them as building materials. For example, because metals expand when they're heated, when you build a bridge, for example, you have to account for the fact that the metal in the bridge will expand in the summer. It's going to contract in the winter. In fact, here you have these teeth in these bridges. They're called expansion joints. And what they do is they allow the bridge to actually expand back and forth. It can slide in this direction, or it can slide in that direction. And it's all because of this expansion when it's heated. All right. Now, scrolling down, let's go through a few sample problems here. A copper penny has a mass of 3.1 grams and a volume of 0.35 cubic centimeters. What is the density of the copper? Well, again, you can either use density equals mass over volume, or you can just simply realize that the units are going to be grams per cubic centimeter, and then get these numbers to line up. I'm just going to plug the numbers in. 3.1 grams divided by the 0.35 cubic centimeters. And when you perform that calculation and round to the 2 sig figs, 3.1 divided by 0.35 gives us a density of 8.9 grams per cubic centimeter. All right. Next sample. A student finds a shiny piece of metal that she thinks is silver. It has a volume of 245 cubic centimeters and has a mass of 612 grams. Calculate the density and determine if the metal is in fact silver. So once again, density equals mass per unit volume. So we're going to plug in the numbers. 612 grams divided by the 245 cubic centimeters. And when you take your 612 divided by your 245, you're getting, 2.5. Actually, you go to 3 sig figs, so it's going to be 2.50 grams per cubic centimeters. And in fact, if you scroll up to a list, does silver have a density of 2.5 grams per cubic centimeter? Well, according to this table here, silver doesn't look like silver's on here. I can tell you that silver has a density that's going to be much higher than that. Silver has a density, I think, that's going to be over 10. This has got a density that's much closer to aluminum, so no, not silver. All right? And in the final example here, it says what is the volume of pure copper coin that has a mass of 20 grams? The density of copper is 8.9 grams per cubic centimeter. Well, you're looking for the volume in cubic centimeters. You're starting with 20 grams, and so now you're going to be multiplying that by some fraction of this density, or some form of this density. We're going to put the cubic centimeters on top, and we're going to put the 8.9 grams on the bottom. The reason why we're able to do that, or want to do that, is because we want the grams to divide out top and bottom. And so now it is simply going to be 20 divided by 8.9, and we have 2.25. Or if you round to 2 sig figs, it's going to be 2.2 cubic centimeters. That concludes Chapter 3.